Right, good afternoon. This little lecture is on state space analysis. State space analysis was originally invented by the Americans in the 1960s and helped them really with their space program. Although the term space doesn't actually mean space as in space travel, it means something slightly different in this context. It just means the space in which the system occupies what's going on. So let's look at the learning outcomes associated with this lecture. So it's looking how to define a mathematical model called a state space representation for a linear time invariant system, and then how to obtain one as well. How can you actually define it, and also how to get one, and then how to convert between transfer functions and state space models, and also go between state space models and transfer functions. So why did people move into state space as opposed to transfer functions? Well, it turns out it's easier for computers to perform matrix algebra. And so when packages like MATLAB and other things came along, people realized that if you formulated your control system design problem in a matrix format, you could do more advanced analysis. So it became, for advanced control system design, became a more plausible and attractive way of going forward. It can also handle multi-inputs and multi-outputs as well. So if it's a multi-input, multi-output control system, it can cope with that without too much extension. It also provides more information about the system, because in an output feedback control system, you can only see the output. But in the state variable system, you can look at all the different variables that are going on inside the system as well. So it's a more sophisticated design method, and it's used in larger scale flight systems. And probably my favorite state space analysis is something called Kalman filtering, which is used in most flight control systems, and that uses this state space analysis. So let's have a look at our general concepts behind state space. We take generate a set of variables now called the states of the system. Now the states of the system are also closely related to the order of the transfer function. So that means how many poles it's got. So if your transfer function had, let's say, 5 poles, then this system will have 5 states. Every pole in your transfer function is uniquely mapped by a state. And so if there's a 4th order system, you would have 4 states. 10th order system would have 10 states. And the idea behind this is that you've got a input to your system, some initial conditions for your states. You've got your states, got some differential equations in here, and you can use those then to compute what your output is, but also know what all the states in your system are at the same time. And so this is the underlying thinking then behind state space. And for a single input, single output system, we could have a first order differential equation, x sub say x1 dot, which would be some number times x1 and then a number times x2, down to number times xn, where n is the order of the state space, plus some input, u1, another state differential equation representing that one, all the way down till we get the nth order differential equation. And these will now represent our state space first order representation of our state space equations. Now we could write these in matrix form simply by saying that simply that x1 dot is dx1, and then we could say a1 times x1, a12 times x2. So if we take these as a11 times x1, a12 times x2, an times x1 plus b11 times u1. So that into that plus this is equivalent to the first line here in this equation. The second one is x2 dot, and that'd be given by that times that plus the number in there times that, which is that second row, and go all the way down and finally get your last row here would be given by this one times that. So it'd be that times that plus that times that plus that times that plus that times that. And this now is called our state space representation, and we tend to call this big matrix here capital A, this big one here, capital B. And the output state, which we'll look at in a moment, we call capital C. So with state space equations, we have what's called a state space triple, A, B, and C. And this is then the representation of those state space equations. Now, it's possible to go back from these to a transfer function. So that's quite handy. So we could go from a transfer function maybe to some state space, and then from some state space back to a transfer function. That would make sense. So if we take the differentials of these now using Laplace transforms, then x dot would be s times x, and x would just be x, and that would be u. So we could rewrite this equation with the x dot as s times x, and then we could say that that would give us this equation here. We could then take the ax onto this side, take x out as a common factor to get down to here. Now we need to get rid of this term here. We can do that by multiplying by the matrix inverse. So if we multiply the matrix inverse by this, it disappears, but the matrix inverse appears here. So that's this bit here. But then the output y is given by c times x. Going back to here, y is c times x. So the output y is c times x, will be c times this. So y is c into si minus a to minus 1b times u. And our transfer function is given by y as something times u. So therefore this part here must be the transfer function. This gives us a interesting little formula for the, there's our state space equation there. This is the formula for going between transfer functions, or state space and transfer functions. So it's c into si minus a to minus 1b. Now this is not too bad, except for the fact that you've got to work out the matrix inverse here. So that could be computationally quite tricky for you to do in your head, but it's possible to do. So let's look at some simple state space analysis now. You've got transfer function 3 over s plus 6, output x1, input u. So you can say x1 is this box times the input. So given x1 is 3u over s plus 6, then move the s plus 6 up here. So we get s plus 6 times x1 is 3u, but s is d by dt. So d by dt of x1 is x1 dot. 6x1 on the other side is minus 6x1 and 3u. So you can think of it, this is a transfer function, and this now could be a first order state space set of equations. First order mean it's a scalar case. So in the scalar case, quite quick to go from transfer functions to state space. If we look at a slightly more complicated version, we've got 3 states now, x1, x2, and x3. Remember, for every pole, we have to have a state. So there's the state associated with that one, there's the state associated with that one, there's the state associated with that one. We then say that x1 is this times this to get that equation there. Then say x2 is this times this to get that equation there. And x3 is that times that to get that equation there. So we've got these 3 equations now representing this transfer function. We also know in this particular case the output is y, but the output is also x3, so y is x3. So we've got this little expression for the output. We can use that to work out the c in a moment. But coming back to this now, we've got this expression here. So if we take this term here and move it up there, take that term there, move it up there, take that term there, move it up there, we get these following 3 expressions. Now s times x1 is x1 dot, the 6x1 becomes minus 6x1 and the 3u remains the same. S times x2 becomes x2 dot, 2x2 becomes minus 2x2 on the other side, 4x1 remains the same. S times x3 is x3 dot, 3x3 is on the other side and minus 3x3 and the 1x2. So we've now got 3 first order differential equations. Now if we collect these together into a matrix form, out will pop our state space equations. So here are the 3 equations here. So x1 dot now is minus 6x1 plus 3u. That's that one. x2 dot is minus 2x2 minus 2x2 plus 4x1, 4x1, no u. x3 dot is given by an x2, so that's 1x2 minus 3x3. So you can see now you can go from there to the structure here. We also need that y, that should be y there, shouldn't it? y is given by c times x. So, but y was equal to x3, so that's going to be that times that plus that times that plus that times that. So that's telling us that y equals x3. And there's our state space representation now of this system. So that's how we could go now from a set of transfer functions to some state space equations. Finally, we might want to go back now from our state space equations back to our transfer function. So in order to do that, we'll have to use this slightly complicated expression here, and we're going to have a go at that next. So, don't know what it does here. It's a bit annoying, this. Every time I use this PowerPoint, it changes the size of these things. I'm just going to do a bit of tinkering here. There we go. Even this one gets changed in size. Don't know why. Right, so here's our expression now for the transfer function. Here's our a, here's our b. The c is given by 0, 0, 1. So we now need to work out c into si minus a to minus 1b to get the transfer function down here. So the c is 0, 0, 1. The b is 3, 0, 0. Now si minus a to the minus 1 is going to be s, that's the si, and then minus a, so that's 6. Minus 6 becomes plus 6, the 4 becomes minus 4, the 2 minus 2 becomes plus 2, the minus 3 becomes plus 3, and then 1 becomes minus 1. And then that's inverted here. The problem now is we have to invert this matrix. Now, in this particular case, we have to work out therefore the adjoints, because it's the actual transfer function is c into the adjoint of si minus a to minus 1b divided by the determinant of si minus a. I'll just move that along a bit like that. There we go. So the first thing we could do is maybe work out the determinant. So because it's got a naught there and a naught there and a naught here, the determinant is just that times that times that. So it's s plus 2 times s plus 3 times s plus 6. So that's the bottom line, our determinant. And now we've got to work out the adjoint of si minus a to the minus 1. So that there potentially could be 9 adjoints here. But we don't need to work them all out. Because if we look at it, when we multiply this into this, get that times that plus that times that plus that times that. So it's only the bottom line really that counts. And when you multiply this into this, and this into this, and this into this, it's only the first column that counts. So only the first column and the final row counts. So it's this element that we want. But we don't want that element because it's transposed. And it's transposed here. So the transpose this is up here. So we need the adjoint of this one. So the adjoint of this one is this times this minus that times that. It goes on a plus minus plus, so it's going to be plus. So minus 4 times minus 1 is 4, and then 4 times 3 is 12. So we can go from here now to our transfer function, which is 12 of s plus 2, s plus 3, s plus 6. And if we notice, that is what we've got here. 3 4s are 12 of s plus 2, s plus 3, s plus 6. The order of these doesn't really matter. So that tells us now how to go from, what we looked at here now is how to go from some transfer function to some state space equations, and then how to go from some state space equations back to the transfer function. Now, one extra thing we need to know about state space equations is that state space equations aren't unique, which means that there are an infinite family now of these A, B's and C's. Now, with an infinite family, some family members are going to be not very interesting, and 1 or 2 family members might be interesting. So there are 2 family members that we particularly find useful. One is the companion form, which gives us a very quick way of getting state space equations without thinking too much. and secondly a modal form where the A matrix is diagonal. There's some advantage in having a diagonal A matrix, because when you come to work out an inverse of a diagonal matrix, it's very easy. It's just 1 over the individual elements. So there's an infinite family of state space equations, a unique transfer function. But at that infinite family, 3 or 4 state space representations are widely used. One's companion form, observable companion form, and modal form are 3 particularly useful ones that we'll meet as we go along. So that's a little introduction to state space equations. Right, so here we're going to look at the companion form of a state space representation. This one's particularly handy because it gives you a very quick and easy way of going from a transfer function to some state space equations. So let's have a look at the general technique. Imagine now we've got this transfer function here, which is an nth order transfer function. So it's got an s to the n down there. Then this is a1, the first coefficient is a1, last coefficient is an, and we've got 1 less 0 than poles. So this is b1 s to the n minus 1 all the way down to bn. So we could take this transfer function and split it into 2 parts by putting the bottom half on the left hand side, the top half on the right hand side, calling this intermediate variable in the middle x. And this is the trick now to doing some analysis. So the first thing we'll do is just analyze this bit, and then we'll analyze that bit to build up the whole picture. So looking at this part here now, we could say that this is this times this to give us this little equation here. We'd also say that this is this times this to give us the second equation. So the first equation we look at is this variable here, is this box times this input. So here's, and then we're going to call the variable x1. So x1 is over u is 1 over this. So if we move the u now up here and move this term onto this side, then if we differentiate x1 n times, s to the n will differentiate it n times, then this one won't be differentiated at all, so it'll just be this times x1, that's equal to u. So that gives us now a differential equation, an nth order differential equation representing this system. We've got that by moving this up there, that up there, and then differentiating s to the n is dn by dt to the n. So that's our first little trick. The second trick now is to say that dx1 by dt is x2. So that means this first term, the first term is x1, but the second term now, this dx1 by dt, we're going to call x2. So that's actually going to become x2 in a moment. And the next term, which will be, it's missing here, but would be d2x1 by dt squared, you can go x3 and fill them up that way until we get to this term here. And you can notice that this is one bigger than this one here. So x to the n, this will be d to the n minus 1. So that'll be d to the n minus 1 will be xn. And then d to the n of x1 we can write as xn dot, because if we differentiate this once more, this will go up by an extra d to become, so the minus 1 will go to an n. If we differentiate this, it's like putting a dot on top of it. So I could rewrite this equation now as the following. This is the d to the n x1, d to the n minus 1, all the way down to dx1 to no d's. So there's the equation we had. Now we can now replace now these terms by the first term by x2, then x1, or x1, x2, x3, all the way down to xn, and this is xn dot. So we've got an equation now with xn dot, with xn in it, xn minus 1, xn minus 2, down to x3, x2, x1, and the u. So this equation now can form one of the equations in the bigger state space equation. And it forms the bottom line here.
So we get xn dot is minus an x1 minus an minus 1 x2 minus an minus 2 minus an 1 times x1 plus u. So this line here now, notice the negative signs in here, and the an is associated with the x1. So that's why this is the an has come up first, because it's associated with the x1. We also know that dx1 by dt, which is x1 dot, is x2. And so if we go to here, we know that x2 dot, or x1 dot, sorry, x1 dot is x2. So x1 dot is x2. So go back to here, we've got x1 dot is x2. We know that x2 dot is x3. So we also know that x2 dot is x3. So if we go, that allows us now to put x2 dot is equal to x3. It'll be the third one down. And finally, xn minus 1 will be xn. So that means that we get the matrix here. This top half is completely zeros, but there's a 1 going down here, which is 1 off the main diagonal. This is called the main diagonal down here, and this is 1 off the main diagonal. So we get some parameters going down, some 1s going off the main diagonal, and then we get these numbers here now, these numbers here going along there in reverse order with negative signs in. So this is a promising approach. To get the A matrix, we fill it with zeros. We put a 1 down in there in the B. We fill it with zeros. We put 1s on the main, 1 off the main diagonal all the way down. Then these numbers here now are these numbers here in reverse order, but with negative signs. So that's a quick way now of getting us our A and B. And then we need to get our C. So the C now has the first part. So this is where we get the C from. Remember, we use this to get the A and B. Now we're going to use this part and this equation here to get at the C. So in this case now, we've got y, the output, is given by this times x1. So bn x1 is bn times x1. And then bn sx1. Now sx1 is x2. So that's the same as x2. So bn minus 1 gets multiplied by x2. That's bn minus 1 times x2. And we could go all the way down here. That's the next one's going to, till we get to the very end. So it's going to be b1 times xn, bn minus 1 times b2. So what we've got in this case now is to get these numbers here, we've just literally written those numbers in reverse order. And that's giving us the C. This is coming from the idea that the C is given by this expression here, which is given by bn x1, so that's going to be bn times x1, bn minus 1 times sx1, but sx1 is x2, so that's the second state. So it's going to be bn minus 1 times the second one. Then the third one would be bn minus 2 s squared x1, but s squared x1 is x3. So it's going to be the third one, x3, times the third term. And they'll just fill in this way as they fill in and pick up those coefficients. So to get the C, all we've got to do is take those numbers there and write those down, positive signs, but in reverse order. And that gives us then some state space equations. So let's have a look at this. Here's a little example. S plus 3, s squared plus 3s plus 2. So it's a second order system, so it's a 2 by 2 state space. We put a 0, 1, 0, 1 in there. This is a 0 there, 1 off the diagonal, 0, 0's here and 1 at the bottom. And then we put these numbers here in reverse order with negative signs here. So it's minus 2, minus 3. And then these numbers here go along here in reverse order with positive signs. So it's 3 and 1. And so we go quickly from our transfer function to our state space. So we'll do some more examples of these as a little tutorial next.
Right, today we're going to look at a little state space example. Here's a transfer function, 6s plus 1, 4s plus 9, 1s plus 10. And what we're going to do is to convert this into some state space equations. X dot is Ax plus Bu, y equals Cx. The first thing to look at is that there's 3 s's, 1, 2, 3. So we know that there's going to be 3 states in the system. So we could put down our state space equations as x1 dot, x2 dot, x3 dot. So the matrix here is equal to, so now there's going to be a 3 by 3 matrix here. So times x1, x2, x3 plus something times u. So there's our format for our state space equations, and there are a variety of ones we could get in here, but what we're going to do in the first instance is we're going to label this variable here x1, that one x2, and this one x3. So we use the outputs from each block as a state in the system. And so we'll also need a little equation here that y equals something times x1, x2, x3, and we can immediately get what the y equation is because we know that y is x3, so that's going to be 0, 0, 1. So y is that times that plus that times that plus that times that. So that's a matrix equation of y equals x3. So the first thing we do now is we take the first little block. So we've got something like this. Here's our first block. We can say that x1 is equal to 6 of s plus 1 times u. So this is this times this. We can then move the s plus 1 up here. So you get s plus 1 times x1 is equal to 6u. Now s, remember what s represents? S represents d by dt. So s times x1 will be x1 dot. So get x1 dot plus x1 equals 6u. And then we can move the x1 onto this side. As it goes over, changes sign. So your x1 dot is equal to minus x1 plus 6u. So we're going to try and fit this little equation now into the first line of our matrix equation. So x1 dot is x1 dot here. It's minus x1, so there's the x1, that's just minus 1, no x2s and no x3s, and we've got a 6u, so we get a 6 in there. And there's our first line now of our A matrix. So we're going to do the next one now. The next one we take the second block. So put the second block down. This time x2 is coming out and x1 is going in. And we've got a 4 of s plus 9. So x1 is going in, x2 is coming out, 4 of s plus 9. We can then say that this is this times this. So you get x2 equals 4 of s plus 9 times x1. Move the s plus 9 up here. So you get s plus 9 times x2 equals 4x1. S times x2, x2 dot. So you get the x2 dot is 4x1 minus 9x2. The 9x2 on this side changes sign. So this equation here now gives us the second line. So it's 4x1, so it's going to be 4x1, minus 9x2, and 0. There's no x3s, and in this case, there's no u's. So that's giving us 2 now out of our 3 lines for the state space equations. And the last one is going to be 1 over s plus 10 x3 coming out, and we've got x2 going in. So we can say that x3 is 1 over s plus 10 times x2. So this is this times this. And then we can move this term here up here. So we get s plus 10 times x3 equals x2. S times x3, x3 dot. So we get x3 dot is x2 minus 10 x3. So x3 dot now is x2 minus 10 x3. So there's no x1s, that's a 0. There's 1 x2, and minus 10 x3. And there's no u's. And so we've now gone from our state space, or transfer function even, to our state space equations. Now what we might have done is, there's a wasp coming here, one of those bit me yesterday. Sure, I just get it, sorry to be, no, I missed it. I'm not a good shot. If we multiplied all this out now, we get 6 4s 24. Get 24. If we multiply s plus 1 times s plus 9 times s plus 10, I'll get s cubed plus 20 s squared plus 109s plus 90. So this is the, if I multiply that by that by that, you can check some of these numbers because that one will be that plus that plus that. That number there will be that times that times that. And to get that number, it's that times that plus that times that plus that times that. It's the product of the three things added up. Anyway, that's our transfer function. So this now, we might have it in this form rather than this form. So we could do this one now using our companion form. So this is, if we rub these numbers out here, like that, and I just put some boxes back in. And then we've got different ways of getting state space equations. So one technique now is the companion form. So it's the third order system, so the three-state thing. Then in companion form, we'll put in a 0, 1, 0, 0, 0, 0, 1, 0, 1. So we fill in the top completely with zeros, put a 1 down there, and put a 1, not in the main diagonal, but 1 off it. And that gives us the starting off structure for our companion form. Then the numbers that go along here are these numbers here in reverse order with negative signs. So that's minus 90, minus 109, minus 20. And these numbers here is that number there. So imagine that's like we've got no s's. There's no s squareds. So it's these numbers here in reverse order. So it's going to be 24, 0, 0. And there's our alternative now, state space representation. So we've got one which could have used the states x1, x2, x3, or we could have done it in companion form. These states now are not the same states. The matrices are correct, but they're not the same states. The variables x are not the same in both problems. But it shows you how you can go from transfer functions to state space equations. Thank you. Hi, good afternoon. This little revision lecture is on state space, and the first part of state space is just that we can start with a transfer function gs, and we have to convert them into some state space equations. The one of x dot is x must be u, y equals cx, and these are then called state space equations. Now, there are a variety of state space equations, but one that's particularly useful to know is the companion form. This is relatively straightforward to do and gives you a quick way of going from a transfer function to some state space equations with minimal problems. So I thought we'd do 3 examples here how we could do this. So we've got a transfer function, say gs given by 6s plus 2 over s squared plus 2s plus 9. And what I want you to do now is obtain some state space equations in companion form. The first thing we do is look at the number here. So it's number 2. So it's a 2 by 2 state space representation. So we're going to have x1 dot, x2 dot. Then we're going to have a 2 by 2 matrix here. x1 and x2 plus another matrix here times u and y times x1, x2. Now, what we've got to do is put some numbers in here. So in companion form, we put a 0 and a 1 and a 0 and a 1 in there. So we fill in this with zeros, put a 1 off the diagonal and put a 1 in the bottom box down there. We then put these numbers here in reverse order in there. So it's going to be minus 9, minus 2. And then these numbers here go in reverse order here, 2 and 6. So this is a state space representation of a transfer function in companion form. So do another example. Let's say gs is given by s squared plus 4s plus 1 over s cubed plus 6s squared 11s plus 9. So this time it's a third order polynomial. So it's rather than having 2 states, we're going to have 3. So it's going to be x1 dot, x2 dot, x3 dot, and here this time have a 3 by 3 matrix times x1, x2, x3 plus something times u and y will equal to x1, x2, x3. Like that. So it's a similar technique to this. So we put in a 0, 1, 0, 0, 0, 0, 1, 0, 1. So this fills it with ones, with noughts, one's the bottom. This fills it with zeros, but there's a 1 off the main diagonal. Then these numbers here and these numbers here in reverse order with negative signs. It's going to be minus 9, minus 11, minus 6, and sorry, that's in the wrong box. Unfortunate. So it's going to be minus 9, minus 11, minus 6. So it's, these numbers here have done this completely wrong. These numbers here going here in reverse order with negative signs. It's minus 9, minus 6, minus 11. And these numbers here are these numbers here in reverse order. So it's 1, 4, 1. So that 1 goes in there, that 4 goes in there, that 1 goes in there. So it's a reverse order. So this is these numbers here are those numbers there in reverse order with negative signs. Let's do one more example. Let's say gs is given by 6 s cubed plus s plus 4 over s to the 4th 12s cubed 18s squared 6s plus 17. So this time it's a 4th order system, so it's going to have a 4 by 4 state space. So we're going to have x1 dot, x2 dot, x3 dot, x4 dot, and then we'll have a 4 by 4 matrix here now, times x1, x2, x3, and x4, plus something times u, and we'll have our y will be given by a 4 times x1, x2, x3, x4. So let's move on here. So the technique is we put in a 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and a 1 in there. So this all fills up with zeros, 1 down there, 1 here, 1 off the main diagonal. Then I'll try and get it right this time. It's these numbers here go along there, along here in reverse order with negative signs. So it's going to be minus 17, minus 6, minus 8, minus 12. So that's minus 17, minus 6, minus 8, minus 12, in that order there. And these numbers here go in here in reverse order. So there's a 4, and there's a 1. Now there's no s squared, so that's a 0 in there. And there's 6x cubed, s cubed, yeah. So it's going to be 4, that's the 4. There's the 1, there's no s squared, so that's a 0, and there's 6 of these. So this is the technique now, general technique for converting state space equations, or transfer functions even, for converting transfer functions into state space equations in companion form. And as you could expand this out to any size of system you wanted.
Hi, good afternoon. This is looking at closed loop state space equations, and one of the main advantages of state space is that by posing it as a matrix form we get a standard solution which is very simple, and so it's attractive from that point of view, especially if you can hand it over to a computer program like MATLAB. So doing closed loop state space equations is not something that you'd really want to do by hand. It's something you'd want to do using MATLAB. So this is some little bit of work now on using how to develop closed loop state space equations. So we're going to look in this particular case at what's called output feedback. That means the control U would be given by K into V minus Cx. Remember that Y is Cx. So the output is Cx, but rather than having this as Y now, we can replace it by Cx, where C is coming from our state space triple in the ABC. So here we have our state space equations, and here we have, now in state space they tend to call the equation for U the control law. Just a bit of terminology they use, and there's different complexities of control law. So what we're looking at is the simplest, which is always the best place to start. So U will be given by plus K, actually be given by K into V minus Cx. So this will now be our little block diagram of what's going on. So for x dot, this x must be U. U is K V minus Cx. So we can put the U now into here. So that's going to be B times this. Let's be BKV. That's the BKV, and you're going to get a B, K, and a minus C. So minus. Now the order is important in matrices because A times B is not the same as B times A in matrices. So you've got to keep the order. So it's going to be B times K times C, but with a minus on. So it's going to be minus. So I should have had a minus in there. Minus BKCX. So we get now x dot is AX, that's the AX, minus BKCX, that's minus B times K times CX plus the B times the K times the V. So this now is our closed loop state space equation, and we can take X now as a common factor. So we get X dot, there should be X dot here, I can't get my computer to do dots here, but it's x dot is A minus BKCX plus BKV. So this now is the closed loop state space equation. Notice how much easier this is than from doing the normal feedback that we might have done in a block diagram. It just becomes a simple equation in terms of the new state space A matrix is given by A minus BKC. So this is the open loop state space equation,
and these are closed loop state space equations. So A minus BKC is the new A matrix for the closed loop system. This is open loop, this is closed loop. And one of the things that we can do is we can work out the stability of this system by working out the eigenvalues of this matrix here. So if we go to the matrix, the eigenvalues of these, we can define the eigenvalues of the determinant of Si minus A plus BKC. It's minus this, so that becomes a minus, that minus becomes a plus. And if we work out this gives us the characteristic equation, but if we worked out the eigenvalues of this, which are the same as the characteristic equation, we get the same equation as if we'd done the closed loop stability equation, PS plus KZS. So this is a quick way now at getting at PS plus KZS. You just look at the eigenvalues of A minus BKC. So this is quite attractive. So let's just have a quick look at this. Here's say a third order differential equation. We could convert this now into a transfer function, and we could say that x1 dot is dy by dt, x2 dot is d2y by dt squared, x3 dot is d3 by this. So we get that this would be x3 dot, this would be 5, well, that would be equal to u minus 2y minus 3 x2 minus 5 x3. So that gives us the x3 dot equation here. We know that x1 dot is x2 and x2 dot is x3. x1 dot is x2, x2 dot is x3. So there's our state space equations, and we know that the output in this particular case is given by x1 because it's in companion form, so it's going to be 1, 0, 0. So we've now got our A, B and C here, because we made y equal to x1. That was the trick at the start, we just made y equal to x1. That's why that's y equals x1. So then we could then formulate A minus BKC. So we could do this in MATLAB, and if we put a k in, it would come out, just put the k in, put the k, can't see it here, but it's inside the, so it's BKC, and this now would be the closed loop state space equations. And by looking at we could look at the eigenvalues of this for different values of k, and that would tell us how its stability changed. So here's the actual equation, and what we can do now, this is a little piece of MATLAB code, chooses a value k, here's the A, B, C, it works at A minus BKC and then works out the eigenvalues. So these now are the same as the closed loop poles. So with k as 4, you can see it's all stable. With k as 14 though, it's just gone unstable because these have just gone positive. Notice when it's 4, these are negatives, it's all negative stable. 14, it's gone unstable. If we have 13, it's marginally stable. So we know now this system was marginally stable at a gain of 13. We could have got that through a variety of ways, couldn't we? Could have done a Hurwitz stability test, could have done a root loci, but this is how you could do it using state space. You just formulate A minus BKC, choose a value for your k, and work out the eigenvalues. So difficulty with eigenvalues is that you and I can't work out eigenvalues, they're too hard. But if you've got a computer, it can do it in a jiff, like 1 millisecond. So if you've got MATLAB at hand, that final command there, which is tricky for us, it can do without even thinking. So here's a little bit of MATLAB code, ABC. I've also worked out I've done a state space to transfer function, so I've converted it into a transfer function as well. So I know what the transfer function is. I've then set up my state space equations here, the open loop state space equations, put them into feedback control, taken the numerator and denominator from the same system, put that under feedback control, And I've also worked out the closed loop state space equations here. So here's my ABC, and then I worked out A as the closed loop A, ACL as A minus BKC, BCL as BK, and C remains the same and D remains the same. So armed with those now, I can now set up this little system. This is the original open loop state space. This is the closed loop state space here, which has got no feedback around it because it's the closed loop state space, and this is the original transfer function with the same feedback in. So we've got three little systems here now. One here, the feedback normal transfer functions, state space open loop here but with feedback around it, and then here we've worked out the closed loop state space equations and stuck those in there. Now if you run this in Simulink, you'll find out all are exactly the same, showing that this system here now is the same as the closed loop system here. And notice how simple this expression is. That's the beauty of it. It's very simple and it's always the same. That should have been a dot in there, unfortunately. But it's always the same, and all you're going to change is the A, B, C, and K. So you can just define what the A, B, C, and K is, and this one bit of code will do it all for you. So that's the beauty now of closed loop state space. Good if you've got MATLAB, not so good if you haven't. And there's an example of this in the MATLAB sets of tutorials, so I suggest you have a go at those and then you'll get a better understanding of this. Thanks. So we're still on state space, and another method that we can deploy is if we've got a block diagram of the system, we can convert this block diagram into a set of state space equations of the form x dot is ax, bu, y equals cx. And the basic thinking behind this is to do each block in turn and label each output from the block as a state. So you've got a block with an S in, so we could label that, say, as x1. You've got another block, label that x2. This one x3, and this one's going that way, so it'll have to be x4 because the signal's coming down this way. So as an example here, let's say we've got this block here and we've got some signal coming in. In this particular case, this would be V minus x4. So this would be V minus x4 going into the block. That's that signal there, and it's V minus x4. We've got x1 going into these, and into this one we've got x2 plus x3 going in. So we get those off the block diagram. That's V, that's x4, so that's going to be V minus x4. This is clearly x1. These two add together to give you this one, so x1, x2 plus x3 going into this box. Because it's got four variables, we can have a 4 by 4 state space, so it's going to be x1 dot, x2 dot, x3 dot, x4 dot. So we're going to have a 4 by 4 matrix here. Times x1, x2, x3 and x4 plus 1 by 4, 4 by 1 even times v, and we have y equals something times x1, x2, x3, x4. So there's our state space representation. Let's that one. Now to just put some little boxes down for us to fill in now these boxes to get our state space equations. So we start off by picking each box at a time, figuring out what's going into the box and what's coming out of the box. So this one now we said x1 is equal to 6 over s plus 9 into v minus x4. So this is this times this. Then we can move this term here up here to s plus 9 times x1 is 6v minus 6x4. Now s is the same as S represents d by dt, that's the trick here. So s times x1 is x1 dot. So you get x1 dot. Then 9x1 on the other side becomes minus 9x1. So it's minus 9x1 minus 6x4 plus 6v. So this is now our first little equation, and this goes on the first line here. So x1 is minus 9 times x1, no x2s, no x3s, minus 6 x4s and 6v. This is saying this is that times that, plus that times that, plus that times that, plus that times that, plus that times that. And there's our first bit of the state space completed. We can now move through each of the boxes in turn. So let's do this for next. So our next little box has got x1 going in, x2 coming out, and this is 1 over s plus 2. So now we can say this is this times this. So get x2 is 1 over s plus 2 times x1, and move this up here. Get s plus 2 times x2 is equal to x1. Now s is d by dt, so s times x2 is x2 dot. 2x2 on this side will be x1 minus 2x2. So here's our second equation now. x2 dot is x1, so that's going to be 1 in there, and then minus 2x2, and then 0 everywhere else. So x2 dot is that times x1, that times x2, that times x3, that times x4 plus 0. And there's our second line of our state space. Now go for the next one, which is going to be this one here. So this is similar to the one we've just done. This time it's got x1 going in, and this time it's got x3 coming out. There's x3 there, and it's got a 4 over s in the box. So this now is this times this. So x3 is equal to 4 over s times x1. If we move the s up here, s times x3, x3 dot. So x3 dot is 4x1. This is a nice easy one to do now. So x3 dot is 4x1, so it's going to be a 4 in there, 0, 0, 0, and a 0 in there. Then we have one more to do. This one has got x plus x2 plus x3, and this is x2, x plus 3. These are added together, fed around that way. So I've got a last box now with x2 plus x3 going in, 10 of s plus 9 in the box, and x4 coming out. So x4 is coming out. So x4 now is equal to 10 of s plus 9 times x2 plus x3. Then move the s plus 9 up, so you get s plus 9 times x4 is 10x2 plus 10x3. But s times x4 is x4 dot. Okay, x4 dot is equal to 10x2 plus 10x3 minus 10x minus 9x4. Remember, the plus 9 on this side becomes the minus 9 on that side. So that gives us our last little equation now. There's no x1s this time. We've got 10 x2s, we've got 10 x3s, and minus 9 x4s, and no u's. The last thing to do is get an equation for y, but clearly y is the same as the output here. So y is equal to x2 plus x3. So we can get this from this equation. So y is no x1s, there's no x1s. There's 1x2. That's coming from the 1 there. There's 1x3 coming from the 1 there, and there's no x4s. And then this gives us, here's our block diagram, states x1, x2, x3, x4, and this is now a state space representation of the system with a 4 by 4 state space equation. So I hope you found that useful. Right, so let's have our learning outcomes review, and this will allow us to understand now how to define a mathematical model called a state space representation as an A, B, C and possibly a D for a linear time invariant system. You should also know how to obtain a states representation for a linear time invariant system from either some initial differential equations or from a transfer function. You know how to convert between transfer functions and state space models, and vice versa from state space models to transfer functions. And finally, you also know how to form closed loop state space equations using a simple mathematical equation which is A minus BKC, and then working out the eigenvalues of those. And this is equivalent to forming a closed loop system in block diagrams and then doing a stability analysis on the closed loop characteristic equation. So here's a little knowledge assessment for you. Build up the little control system below in Simulink and simulate it. Convert the transfer function, that's this part here, into state space equations and replace this block with some state space equations. Simulate the system to show it's the same. Form the closed loop state space equations, which will just give you one block with an input and an output, and run that alongside this. And again, they should give you the same answers. And you can compare your three answers and they should all give you the same thing. The only thing that's slightly tricky to do is forming the closed loop state space equations, but I'm sure you can do it. So let's have a look at our retrospective reflection on state space. So think about what are the advantages of state space over transfer functions. Maybe what are the disadvantages of state space over transfer functions. How to convert from one to the other. How easy is it to formulate the closed loop control stability problem in state space, and what are eigenvalues, and what are the eigenvalues of the closed loop system, what do they represent? So have a think about those things. If you understand those questions, then you're a whiz at state space.